Hey students, welcome to lecture 11 of Linear Algebra 2. So today we want to start with a new topic with so-called continuous dynamical systems, and these can be seen as a continuous version of an example we did last time. Namely, last time we had this example of the population behavior in Japan, where we had in 1 year this distribution of different age groups in the population in Japan, and these we could write down into a vector. And then, knowing the survival rates for one generation and also the fertility rates, we could describe the population behavior by multiplying this vector with this Leslie matrix, and then we obtained the population behavior after one generation. And this is an example of a so-called discrete dynamical system. So let me write this down here. So this is a discrete dynamical system. And today we want to talk about continuous dynamical system, where we do not just consider these times at different generations, but we will be interested in the behavior of something in a continuous way. So instead of talking about vectors for single t's, we will talk about functions. So let me do an example to explain the difference between discrete and continuous dynamical systems in an easy example. So for example, assume you have a savings account at some bank, and there are two ways the bank can offer you the savings account. So one way would be to offer you a discrete version of the savings account, which means, for example, here, assume we have an interest rate of 7%, and annually, meaning after each year, you apply this interest rate to your current savings. So this means that if we would say that if xt is a money in year x, in year t, then xt plus 1, well, 7% means you multiply with 1.07 of your current money, which is xt. And this you do after 1 year. And then you see this is similar to this population example. And this means that this is a discrete, because this you now do so you start with 0, 1, 2, and so on. And another offer would be to say that you have an interest rate which gets applied continuously, so not just after each year, and also not just after half a year, but continuously. And this means that we don't have this equation here, that after 1 year we multiply with a number, but now we have a function xt, money at time x, at time t, and now having a continuous interest rate, this means that we know the change of this function, and the change of the function is given by its derivative. So this means that the derivative of this function is given by multiplying, in this case with 1.06, the current value of your function. So we get this differential equation here. And in both cases, you might be interested in, well, how much money do I actually have after 10 years? So in the discrete example, it's easy to see that xt after t years is just you multiply t times with this 1.07 with your starting money. And in the continuous example, we need to ask what kind of function satisfies this differential equation here. And this we already had as an example, and we will also talk about this in a second. But here we see that one solution would be given by saying that this function here, e to the 1.06 t, so if I take the derivative of this function, then I exactly just multiply with this vector. And then here we also, in the year 0, we have some starting money here. And then in this example here, you could ask yourself which of these two offers is actually better. So you need to compare what is, for example, x of 1 in this example here and x of 1 in this example, and one of these two options are better. But this is maybe an exercise for yourself. Okay, so and this is now an example of a continuous dynamical system, and in both of these cases are the one-dimensional example. So this is a one-dimensional example of a discrete dynamical system. So in general, what do we mean then by a continuous dynamical system? So in general, we will be interested in functions from r to the n, which you should think of being just a vector where in each entry you have a function depending on some variable t, and t you should think of always being some time variable, and all of these functions all of them should have a derivative, so they are in this space C1. And now what we want to consider to be a continuous dynamical system is we define its derivative vector, meaning we take the derivative of these entries. So in each entry we have just the derivative with respect to the variable t. And then having some matrix A, n by n matrix, what we mean by a continuous dynamical system is an equation like this. We want to solve that this vector equals A times this vector here. And you see in the case when n equals 1, then this matrix is just a number. And in this case, this example here is exactly an example of this continuous dynamical system in the case n equals 1. So in general, the goal will be to find a function x, meaning a vector which has n function as entries, such we have this equation. And again, so what is this in the case n equals 1? Well, in n equals 1, A is, well, it's just some matrix with one entry, and this x is just one function. So we ask for the solution of this, as in the example before. And then we know from calculus that there's actually just one family of solutions for this. So if I have some number a, then the only solution to this differential equation here, so if I ask for a function such that the derivative of this function is just multiplying with a number, then we know the only solutions are given by e to the at, and we can also multiply this function with some number c. So we see also, if we use the language of linear algebra, we learned that this taking the derivative is a linear map. And here the question is, what are the eigenvectors of this linear map for the eigenvalue a? And then we see the eigenspace. So the solutions are elements in the span of this e to the at. So this is the eigenspace of the eigenvector, the eigenspace of the eigenvalue a. So we see that in this continuous dynamical system, in the case n equals 1, is completely solved, because we know that there's just this family of solutions, and you can always write it down explicitly. And this will be crucial also for the higher dimensional case, because we will always try to bring it to this one-dimensional case. So, but now let's see what is a continuous dynamical system in the case n equals 2. So we will be interested in in functions like this. So it will be a vector of size 2, where in each entry I have a function depending on t. And first of all, this we can visualize. So for each t, I can plug in different values of t, and for each t I get an element in R2. So I could plot this. So for example, let's say if I plug in t equals 0, I get this point here. So let's say this is t equals 0. Then maybe I can plug in t equals 1, I get this point, and maybe in between I get these values here. So for example, here it could be t equals 1/2. So for each different t, I get an element in R2. And so here this is x at the point t. But what is this vector in this picture? So the derivative So this is the change of this vector here. So we have a curve here, and this vector, this x prime, somehow says at each point in which direction the curve will go. So if we draw this vector here in the picture, then this is exactly the vector x prime t. So at each point I could calculate. So for each t I can calculate this vector here. This gives me the point, and at each t this vector here says tells me the direction of this curve. So what will be the next value if we make one small step for this t. So now so therefore, what if we now consider this dynamical system? So we ask for a solution of this equation here. So if we have some 2×2 matrix A, which is fixed, and now we are wondering what are the solutions for this equation, well, then this means that at each point the direction in which this curve goes is just given by multiplication with the matrix A. So at each point in the plane, we could calculate what it means multiplying this vector with A, and at each point we will get some direction, and then our solution will somehow be moving along these different directions. But let's maybe do an example to make this clearer. So let's assume we have this 2×2 matrix here, 1, 4, 2, 3. And we want to see how does the solution of this dynamical system look like. So first let's rewrite this a little bit. So this just means that so the derivative of the first entry equals, well, so here the right hand side is 1, 4, 2, 3, and I multiply with 1 x1t x2t. So therefore the first entry is x1t plus 4 x2t, and the second entry is the derivative of the second function is given by 2 times x1t plus 3 times x2t. And we are now looking for function x1 and x2 such that this equation here holds. But now first let's do this drawing example. So let's say this is R2, and now maybe let's do a table with different values for x and for x prime. So for example, if the value of x is 1, 0, so we have this point here, then what should this derivative be, well, we can now plug in the values here and see that in this case it should be, well, 1 plus 0, so it's 1, and here it's 2 plus 0, so it's 1, 2. So if this purple thing here is a solution, so a solution means we want to find this curve, then at this point the curve should go next into the direction 1 to the right and 2 up, so it should go in this direction here. So somehow it should go in this direction. And so for example, what is the value at 1, 1? So if we have this point here, then we can calculate x prime is 5, 5, because 1 plus 4 and 2 plus 3. So if our solution would go through this point, then it should go next in this direction and a little bit faster than there, because here the derivative is bigger. And so on. And then for all points here, you could calculate what if our curve goes through this point, in what direction should it go next. So for each point here in the plane, you get some directions. So maybe let's do one more explicit example. Let's see what happens if we have minus 2, 1. If we plug in minus 2, 1, then this is 2 and minus 1. So if we are at minus 2, 1, if our curve goes through this point, then next it should go into this direction here. And then you can do this for each point here, and you will get different arrows like this. And here we will later see that this will look something like this. So this means that if we have a solution, for example, which goes through this point, then we will see that maybe a solution will look something like this. So this will maybe be a possible solution. Because a solution means we can find a function such that at each point the direction satisfies this equality here. So it follows these arrows at each point. Okay, but now before we solve this problem here, let's try to solve an easier problem. So maybe let's first try to solve the continuous dynamical system which comes from this matrix here. So we want to find a function x such that x1 prime t equals, well, minus 1 times x1 t, because we don't have anything here with x2. So we want this equation here. And x2 prime t is, well, here we just have 2 times x2 t. But here in this example we see that's quite simple, because here in this equation we just have something with x1, and in this equation we just have something with x2. So in this case we ask for a function such that the derivative is minus 1, this function. Well, there we know the solution is x1 by this proposition is some constant c times e to the minus t. This function, or this family of function, is the only solution to this equation here, and the only solution to this equation here is x2 of t needs to be some constant times e to the 2t, and c1 and c2 are some constants here. And this was possible because in the first equation we don't have anything with x2, and in the second equation we don't have anything with x1. So both of these are just the one-dimensional case we did before, and therefore we can easily write down this solution here. So in total this means our function x xt is just given by c1 e to the minus t, c2 times e to the 2t for any c1 and c2. And also, so what is x0? Well, if you plug in 0 here, e to the 0 is 1. So these c1 and c2 are somehow exactly the starting points of our curve x. And in this example, if we would draw this thing here, then you would see that so at each point the direction of the curve should be the position of the curve multiplied with this vector here. So if I, for example, if I'm on the x-axis, so let's say I'm here at 1, 0, in this case the direction of my vector should be minus 1, 0. So in this case it should go in this direction. At 2, 0 it should go in this direction, so I get these. And for example, if I'm at minus 1, 0, it should go like this. And if I'm on the x2 axis, then it's just multiplying with 2. So if I'm, let's say if I'm here, then it should go up. In 0 it always should stay the same, like this. And if you plot other points, you will see that at other points it should look something like this. So at each point what I draw now is just I take one point. For example, here, let's say this is the point 1, 1, and I multiply 1, 1 with this matrix. So what is 1, 1 with this matrix? A times 1, 1 is minus 1, 2. So at this point, 1, 1, I should go 1 to the left and 2 up, and this is exactly, or almost exactly, this arrow here. And you could do this for each point, and you see you get this picture here. So if you have some starting value, let's say you take 1, 1 for C1 and C2, then you start somewhere, and the solution will then go in this direction here. And you can also plug in negative t's, and you will see that this here is the case when you say x of t equals e to the minus t, e to the 2t, meaning in this case c1 equals c2 equals 1. Okay, so this is now a really simple example because this matrix A was just a diagonal matrix. But in the example number 1, this matrix A is not a diagonal matrix, and it's not clear how we can solve this equation here, because here it was just clear because these x1 and x2 were independent of each other. But we learned in the last lectures that there's a relationship between arbitrary matrices and diagonal matrices, or more precisely, some matrices can be diagonalized. So this is also the general strategy here. So we know that for a diagonal matrix, this problem is easy to solve. So the strategy to solve such an equation is to diagonalize A. Well, we know this is not always possible, but we will start with this case where it's actually possible. So suppose we can diagonalize A. So meaning that we can find a matrix S such that A can be diagonalized, meaning I can multiply with S from the right and the inverse of S from the left, such that we get some matrix D, which has a diagonal form, meaning they are just the eigenvalues of A on the diagonal. So And this S, we also learned, is given by the matrix where we write in a basis given by eigenvectors of A. So B1, Bn, eigenbasis of A. And so now, how does this help us to consider this dynamical system here? Well, we want to rewrite this dynamical system to another dynamical system. And so what we want to do is we define a new function, u of t, to be S inverse of this vector xt. So in other words, this vector xt is S times ut. So again, x is a vector of functions, x1t up to xnt. And we are given a matrix A, and we want to solve this equation here. And instead of solving this equation, we now want to rewrite this, and we first say, well, we now consider ut, which is given by multiplying this vector here with the inverse of this matrix S. And this matrix S we can get from this matrix A by finding an eigenbasis of this matrix A. So, well, if we do this, if we define ut to be this, so what is then u prime of t? Well, by definition, this is a S inverse times x of t. And here you need to check that this is actually, so when I have this, y is also the derivative of u has this, oh, well, of course here it's x prime now. Why does this also have this relation here? Well, because inside this S there's nothing depending on the t. So if you would multiply this out and take the derivative with respect to t, then you see that you get exactly this multiplication here. And now, well, what is x prime? Well, x prime, we assume that this is a times xt, even though we don't know what x is yet. But this is therefore S inverse times A of xt. And what is xt? Well, xt is S times ut. So this is S inverse A S ut. Well, but this is just d ut, because this here is this diagonal matrix D. So what we have here is now a new dynamical system with u prime equals d times ut. And maybe instead of d, let me really write this out. This d is given by this matrix lambda 1 up to lambda n. But this means again, as in the second example, that u1 prime is just lambda 1 times u1t, and un prime is lambda n times un_t. And also u2 prime is just lambda 2 times u2t, and so on, because here we have again this nice diagonal matrix. But this we can solve, because now they are independent. So the solution is given by u1 prime, u1 t is just some constant times e to the lambda 1 t. u2 is some constant e to the lambda 2 t, and so on up to unt. This is just some constant Cn times e to the lambda nt. So we get a solution for this new dynamical system, because this is one of these easy dynamical systems. But I mean, the goal was to get a solution for our original problem. But here we see that having u, we can go back to the x by just multiplying with s. So we get the solution that x of t we need to multiply with s. So this means we need to multiply the matrix S with the vector C1 e lambda 1t up to Cn e lambda n t. So if we have a dynamical system like this, such that this matrix A is diagonalizable, meaning we can find an eigenbasis of this matrix A, then we can write down this basis into a matrix S, and then a solution to this system is given by taking this matrix S with this vector here, where these lambda 1 up to lambda n are just the eigenvalues of A, and these C1 up to Cn you can choose however you want, but they will determine your starting value, because here you see that what is x of 0, where this is s times the vector c1 up to cn. Okay, so let's do an explicit example for this, or let's solve our original problem here. So in this example here, with this 2 by 2 matrix, we got this difficult looking differential equation here, and now we want to apply this strategy to this problem here. So we need to diagonalize the matrix A and then calculate the solution to this U. So well, let's diagonalize A. This we did several times now. So first we need to find the eigenvalues of A, and for this we consider the characteristic polynomial of A, which in this case is the determinant of 1 minus lambda 4, 2, 3 minus lambda, and this is just 1 minus lambda times 3 minus lambda minus 2 times 4, so it's minus 8. And this we can multiply out, it's hopefully lambda squared minus 4 lambda minus 5. And this we can factor as lambda minus 5, lambda plus 1. And therefore we see the zeros of the characteristic polynomial are minus 1 and 5. So in other words, the eigenvalues of A, lambda 1 is minus 1, and lambda 2 is 5. Or the other way around, however you want to write this down. And then we want to find now a basis of R2, in this case, made out of eigenvectors. So for each of these eigenvalues we need to find at least one eigenvector. So we can calculate the eigenspaces. So the eigenspace for the eigenvalue minus 1, this by definition is the kernel, where we subtract on the diagonal the eigenvalue. So subtracting minus 1 means adding 1, so we have 2, 4, 2, 4. In the kernel of this, so we would bring this to a row-reduced echelon form and see that in this case, well, we can erase this row here by subtracting this and then divide this by 2. So we get that this is the kernel of this matrix, and this is just the span of the vector, for example, minus 2, 1. And the eigenspace of the eigenvalue 5 of matrix A is the kernel where we subtract 5 on the diagonal. So it's 1 minus 5 is minus 4, 3 minus 5 is minus 2, and the row-reduced echelon form of this matrix is 1 minus 1, 0, 0, and therefore this is just the span of the vector 1, 1. And this we could call B1 here, and this we could call B2. And then we can define our matrix S, where we plug in B1 and B2. So this is -2, 1, 1, 1. And then S inverse times A times S equals the diagonal matrix, where on the diagonal we have the eigenvalues, and in this case it's -1 and 5. And this is the matrix what we denoted before as D. And so now we want to use this strategy, and also noticed, I forgot to say, that here in this strategy to solve this dynamic system, we needed to write down S, and here we have this S inverse, but actually at no point in the end we need this S inverse. So here you see in the end we just need this S, so we don't need to calculate the S inverse in any case. So also here, even though we know that this holds, we don't actually need to calculate this S inverse. So first, the solution with the strategy is that our X is the matrix S times, and then some constant times e to the first eigenvalue times t, so it's e to the minus t, c2 times e to the second eigenvalue 5t. So this is -2, so the matrix S is this, and we multiply with this vector here, c2 e 5t. So the solution is given by, where we just now need to multiply this out, so this is -2 times c1 e to the minus t plus c2 e to the 5t, and here we have 1 times c1 e to the minus t plus c2 e to the 5t. And this is a final solution. So for any c1 and c2, this function here, or this curve, however you want to view it, is a solution to this dynamical system. So now so you see in the book, you also see the same example. So here, first of all, what you see here, these two lines are exactly the eigenspaces. So the eigenspace for the eigenvalue -1 was the span of the vector -2, 1, which is this line here. And for the eigenvalue 5, the span was the vector 1, 1, which you see here. And what these arrows here indicate is that at each point, what I did before, these show in the direction. So if I, to get this direction here, this one here, I look at this point. This is a vector, and I can multiply with the matrix A. This gives me this direction vector here. So any of our solution here, so if we choose C1 and C2, so let's do this. For example, when I say C1 and C2 equals 1, then the solution of our dynamical system is given by, well, I just need to plug in 1, 1 here. So it's -2 e to the minus t plus the e to the 5t, e to the minus t plus e to the 5t. So, for example, what is x0? Where this is 1, 1, so it's -1 plus I want another example, sorry. I don't want, so I want C1 to be -1 and C2 to be 1, to make it like the example in the lecture notes. And then here it's a 2 and here it's a minus. So then, so then C0 is, so the starting point of the curve, so to say, is 3. And if you plug in 1, 1 here, 0, 0 here, it's minus 1, so it's 0. So this point here is at 3, 0. So let's assume maybe here is 3, 0. So this is the case t equals 0. And if you would plot this c of t for different t, you will get a curve here, and the curve should move along these arrows. And you will see if you plot it, it will look something like this. So for example, here might be t equals 1, and maybe here is t equals minus 1. And if you let t increase, then the curve goes here, and if t gets smaller, you get this here. But you could also choose different C1 and C2. So for example, if you would choose them such that you get, for example, this point here, then you will see that if you would plot this graph, then it will be something like this. And for example, if you choose both of them to be 0, then you will get, so if C1 and C2 equals 0, of course the 0 solution, if x is the 0 function, then this equation is always satisfied. And then in this case, this curve is just this single point here. And if you choose some C1 and C2 such that you are on the, oh well, maybe orange I already used. So if, for example, if you I have a point on this line here, on one of these eigenspaces, then you will see that the curve runs exactly along these eigenspace, because eigenvectors of this matrix A, so this equation says here that if you are already on this eigenspace, then the direction should also be in this direction, because you have an eigenvector. So you will not go outside this eigenspace here. And also here you see that on this line here, these arrows go in this direction. So if you start somewhere here, you will end up going to 0 here. Okay, so I hope this somehow makes this clear, how these different choices of C1 and C2 give you different solutions in this picture here. And this just means you get different curves. Okay, and this, so there are possible cases in the n equals 2 case. So in our example, we had one eigenvalue. Maybe let's go back to the picture here. The one eigenvalue was minus 1. So this means here in this picture, on this eigenspace, it goes into the direction of 0. And in this eigenspace, we had the eigenvalue 5, which goes outside. And then you see that here next to the eigenspace, it goes in this direction, and here it goes along this eigenspace here. But it could also be that, for example, both eigenvalues are negative. Then both of them would show into the middle. So for example, if I have the matrix 2 by 2 matrix with eigenvalues lambda 1 and lambda 2, then for example in this case here, both eigenvalues are negative, so somehow the arrows all go into the direction of 0, and then, for example, here is one particular solution which always goes to 0. And for example, well, example case B here we had before, one had a positive eigenvalue and one negative eigenvalue. So you go in this direction like this. But it could also be that, for example, both eigenvalues are positive. So then everything goes outside. So if you start at some point, you will always go, if t increases, you go outside of the origin. Okay, so I hope this makes clear what we mean by these different possible cases, and we will also maybe give next time one example of a dynamical system, but we will also then start talking about linear differential equation, and in the homework, which comes next week, you will also solve one continuous dynamical system. See you then.